let's do it. Okay, let's come back to MCMC. We wrote down the algorithm last time. I'll write it down again. We'll kind of think about what the algorithm is. We'll look at an implementation. I'm going to give you the implementation, and my implementation is actually wrong. It's flawed, but you can't tell. So it's part of your upcoming homework set to try to fix it. So I'll tell you what's wrong. I'll tell you which line is wrong. So if you want to use my code, you can use your code. You can use that code and modify it. And I'll refer you to an article that tells you how to fix everything. But we have to get through a few details first before we understand it all. In a nutshell, Metropolis Hastings is all of MCMC. So I will say it this way. I always say that's not quite true. I think what a true statement would be is Metropolis Hastings is the foundation for all MCMC algorithms. So did I say that right? Metropolis Hastings is the foundation for all Markov chain Monte Carlo algorithms. And that, to the best of my knowledge, is true. So all the things that kind of deviate from the exact prescription are, at least has that as a subroutine in it. This algorithm was created in 1953, so a long time ago, in a very specific sort of case. And so I don't think people really understood the utility of it until the 1990s. We'll go through like what actually happened back in the 1990s as well. So Gelfand and Smith got together. Gelfand was on sabbatical working with Adrian Smith, and they carved out the Gibbs sampler paper. So Gibbs sampling is a type of Metropolis Hastings sampling, and I'll introduce you to both of those things in my code. So the code that I'm going to be running is going to be a Metropolis Within Gibbs algorithm, and Gibbs is a type of Metropolis itself. So I need to slow down and tell you what all of that stuff means. Here's the top 10 list. So back in the year 2001, I took a class on the top 10 algorithms, and it covered all of these algorithms. I thought it was really cool. I probably understood Metropolis the least at that time, and now I probably understand it the best out of all these algorithms. Maybe I still understand syntax pretty well. But lots of different algorithms have come about, and some of them are more important than others. And I think what we mean is they're more utilized. So they're used all the time. We're having a discussion about fast Fourier transforms and how cool that algorithm is. We're not going to cover it here. But if you like to think about things in frequency domains, so it's a mapping over to them, and it's a fast algorithm for computing things. I can show you very slowly to compute everything. We won't do that. What I like about the Metropolis algorithm, or Metropolis Hastings, what I keep saying, is that it revolutionized Bayesian statistics. So this is the #1 thing that made Bayesian statistics useful to all of us. So back in the 60s, people used to write down posteriors, and at least say, here's how you would compute a posterior, here's the property of the priors. But in something like a high dimensional analysis, you couldn't actually do it all. You couldn't go through all the integrals, for instance. You couldn't do all the integrations, so you know that there's always an integral in Bayes' theorem. And then computing everything like the expectations and variances and where the area is, that's ultimately an integration problem. And so Metropolis is solving a sort of integration problem that you might learn about like in calculus class when you're learning about quadrature. So there is a connection, and this would be a competitor to doing something like quadrature. So if you guys are interested in quadrature, we could maybe supplement the lecture on that later on. Okay, Metropolis always winds up at the top of the list, and I think it is because it really did revolutionize Bayesian statistics. It made us useful. It made us practical. It made us actually be able to compute what we were talking about, and it changed Bayesian statistics from a philosophical branch to something that's widely utilizable. I think what's important about Bayes so far is it's got regularization in a problem through a prior. So it's got a penalty term built into it, and we know that in a lot of problems that's very useful. But the likelihood function itself has a lot of information, and it jointly characterizes the relationship between all the parameters and the data itself. and it gives it in a conditional form, conditional on the data that you've seen. So I think there's a lot of good things about Bayes itself, but MCMC is the thing that made it so that people could be Bayesians and practice Bayesian statistics on actual problems. Later in this class, I'm going to give you the problem and the papers that Gelfand and Smith originally wrote out back in the 1990s. You might get a good chuckle out of it. So back in the 1990s, the sort of models that people maybe used are a lot different than the models that we use today. But there was an interesting joint analysis problem in doing all the integrals wasn't feasible. And so Gibbs sampling or Metropolis Hastings took rescue. So we'll see that problem in a little bit. Okay. So we've seen this. I just stole this from somebody over at Cornell, Alex Townsend. Thank you very much for your slide. And he goes into what is an algorithm? I think we know what an algorithm is. So does anybody want to answer that question? What is an algorithm? So somebody asks you, what's an algo? I've heard all about these algo things. That sounds pretty cool. What is an algorithm?
Yeah, just a series of steps to be simple.
Yeah, it's a procedure. So it's a series of steps. So that's it. So when I try to explain what an algorithm is, I talk about like cleaning my room or something like that. I have a process. Actually, I never clean my room, but I do clean my kitchen. So I have to do that regularly every night, and I have a process of washing my dishes and all that. So not very exciting. So algorithms are all around us, and we want to come up with efficient algorithms to solve problems quickly. This is a Markov chain Monte Carlo algorithm. So real quickly, what is Monte Carlo? What's that? We've all heard it. This isn't new anymore. So what's a Monte Carlo algorithm? Okay, let me ask a different question. What is Monte Carlo just in terms of the noun? It's a city. Where is it? Somewhere in Europe, that's true. We're honing it down.
Casino in Monaco.
In Monaco, yeah. So Monte Carlo, yeah, exactly. So it's in Monaco. So Monaco, it's kind of like a country. So it's where you go and you like money launder all your money, where all the rich people go. There's lots of yachts around. I've been there. So I couldn't get into a casino though. So it's very formal. I didn't have enough money. They already do. So get out of here. So, the dollar tables are in Las Vegas. There is a class of algorithms called Las Vegas algorithms, and they're related to Monte Carlo algorithms. And so the metaphor comes from gambling, that it's a random process. And so they're randomized algorithms, amortized algorithms, you might say. So, but they're randomized algorithms, so that as you run it, and here's the property of a Monte Carlo algorithm. If I run it for a fixed amount of time, so if I have a for loop with a fixed cap t, so I run it for a fixed number of iterations, I will get a random answer back. So in a fixed amount of time, you get a random answer. There's a little bit more to the story that a good Monte Carlo algorithm is going to be converging in on the truth as well. So the answer is going to get more and more refined and closer to the truth. But as I run it, it's going to be random in a fixed amount of time. That's what Monte Carlo does. Las Vegas is a different set of algorithms. Las Vegas algorithms are algorithms that you don't actually get a fixed answer. You get an answer within some specified tolerance. So I can specify an epsilon and say, I want the answer to be within epsilon, and the amount of time that you need to take is now random. Slightly more to the story is you also impose a probability. You'll say something like, with probability 0.999, I want to be within epsilon. And then you have to wait a random amount of time. And so, for instance, if I were trying to measure the success of something, so maybe I have a coin flip or something, I could think about a coin, and then I could think about maybe estimating P. So, and I flip it some number of times, maybe 10 times, and I do a binomial trial, and then I estimate P with it, and my answer is going to fluctuate a little bit. And every time I run it 10 times, I'm going to get a slightly different answer. That's Monte Carlo. I could say, I want to run this until I get a fixed number of successes. So maybe you say, in order to estimate this thing properly, maybe you can do a calculation and say, I'm going to need to see at least 20 successes before I'm willing to estimate something. And so how long would it take you to generate 20 successes, the fixed number of successes? That would be a negative binomial experiment. And that would describe a Las Vegas process. And so people usually don't like waiting a random amount of time. And so this is an entirely human thing. And so I've got to say, one of my least favorite things to do is to wait, but I really hate waiting when I don't know how long I'm going to wait for. So I think it drives us all totally crazy. So it's like when we were little kids, we'd go to the supermarket or something with our moms. They would say, wait in the car and I'll be back in 10 minutes. And you knew it wasn't going to be 10 minutes, and you didn't even know how long it was going to be. So it was a terrible experience. I still have nightmares about just sitting in the car, waiting and not knowing how long I'm going to wait. Anyway, so a lot of times we don't do Las Vegas just because of that random running time. So if you say to your boss, if they ask you how long is it going to run for, and it's like, I don't know, it could be done in 5 minutes, or it could be 20,000 hours. And so, but you kind of get the idea. If you were trying to estimate something that was low probability, you would need a lot of successes before you were able to estimate it properly. You kind of explored that in a Monte Carlo sort of fashion in the previous homework. And you just kept cranking it up. And that's what people usually will do, is they'll run their Monte Carlo algorithm and run it again and run it again. You could run 3 different Monte Carlo algorithms in parallel. And if the answer was deviating a lot, then you would crank up your iterations, but at least you would know how long you're waiting for. So usually we can get an estimate of what the tolerance is just by rerunning the algorithm over and over again. And I think people usually like to do that. So that's why that dominates the field. Plain Jane Monte Carlo algorithms, not Markov chain Monte Carlo, but just the sort of stuff that you were doing on the homework where you were simulating intervals, that was a Monte Carlo experiment. I was going to say something. Okay, I'll come back around to whatever my strong point was going to be, but plain Jane Monte Carlo algorithms or experiments, if you're trying to estimate like the expectation using Monte Carlo, it's all governed by the central limit theorem. Markov chain Monte Carlo is not governed by the central limit theorem. It's governed by something called detailed balance. And so we'll study that later on. Las Vegas algorithms, if you wanted to come up with bounds on things, use what are called Chernoff bounds versus what you would get out of the central limit theorem. So the theory's quite a bit different. So it's a fun field in itself. So Monte Carlo and simulation algorithms encompass a whole huge field. And what I like about it is that it has all the same properties that we learn in stats classes, but we can control everything. And so we have control over the asymptotics, i.e. we have control over the for loops. Okay. So Monte Carlo, random answer. In fixed time. That's that property. Markov chain. So I think we all know what the Markovian property is, but I'll just write it down so that we're clear. Get rid of this. Markov property. It's just the probability, if we're considering a sequence, like in something like a for loop, the probability of that random variable at time t, conditional on everything that came before it, all the way out to the first time step. I usually start indexing at 0, but in this case I'm just putting a 1 in there, just because that's a little bit more common. This is just equal to this. It's the probability distribution of xt given xt minus 1. So the conditioning on the past only depends on what happened at the last step. And that's the Markov property. So here's an example. So an example of a Markov process. This is called an auto-regressive model. They're very similar to just regression models. So it's something like this. Xt is equal to maybe an intercept plus some coefficient times the last time step plus error t, where this is some sort of independent error, IID error. Very typically, you'd make that normal. So, but if you do change the error distributions, you can get really weird phenomena. So, if this is normal, if error t is normally distributed, maybe I center it at 0 and I just have some random fluctuation, and this coefficient right here, beta, is bounded by 1, this makes the process stationary. So what I mean by that is that at any given time, the distribution will be known, and it's not changing as you move through time, and it converges to something. So if I ended up having this error distribution, and I had a coefficient beta less than 1, imagine this thing was like 10 right here. If this was maybe 1 right here, this is times 10. Let's let that be 0 so I don't have to do an addition. Then this would be something like 10 over here, plus a little bit of error, makes sigma squared small. Then if I take something like 10 and I plug it in, and then I multiply that by 10, this is going to be like 100, plus or minus a little bit. So it's going to start drifting. And it's going to diverge. It's going to shoot off. And if there were a negative sign in front of there, it would oscillate in weird ways, but it would also be drifting, and it wouldn't converge to anything. And so I'll have you play around with this model later on in a future homework. But if you ended up simulating this, if you had some starting point, I'll say that's 1, you might start climbing up to something, and then as I simulate this, and I just simulated this process, it would end up converging to something. And so the distribution at that time point and the distribution at that time point would be exactly the same thing. So the distributions wouldn't be changing. So this distribution might look like this, and this distribution might look like that, if you can see it. Trying to draw some bell-shaped curves in there, they'll look the same. So it would be normally distributed. And so if beta is greater than 1 and equal to, so if you have 1 in there, that makes the process non-stationary. It doesn't converge to the same distribution. If you know the terms like weakly stationary, that just means that the expectation and the variance are the same. So what I'm saying is the whole probability distribution converges to something. So if beta were greater than 1, this would be something like this. I might start somewhere at the first time point, and then this thing would just diverge. So this would be non-stationary, this process. Non-stationary. So a stationary process has the same probability distribution at time t and time t plus k. So a cyclostationary process is one that cycles through and comes back to the original probability distributions. There's a little bit of a period to it. So you think of like a Fourier series or something like that. Okay. So Markov property, we have that. Let's write down what the algorithm is. called Metropolis. It came, I guess it was, what did they say, 1946? So that was 7 years before Hastings got involved in this. And he ended up telling us another variant of this algorithm. And that encompasses basically all MCMC algorithms. So here's the algorithm. So step 0, you initialize the algorithm. So I'm going to consider some probability distribution. Just give us some notation. We use the same notation that we had last time. So here's our target distribution. Our target, I'll at least cast this through a Bayesian lens because we're in a Bayesian statistics class. And Bayesians use this algorithm all the time. There's some posterior distribution. We want to sample from it. So in terms of the example that we're studying, this is theta. Okay, so I'm just calling theta whatever the unknown parameters are in my model. So we want to sample from it. So our goal is to sample from our target. And if we knew how to do it directly, we wouldn't need to do MCMC. Again, the trade-off in MCMC is it's very flexible, and you can usually do this to anything that you come up with. So you come up with some model, you want to estimate all the parameters, that's the name of the game. So we're going to also have a proposal distribution. And it's going to live on theta, so theta will take on the same meaning as that theta. In this distribution, will cover the same space that that lives in, right here. So this will have the same support as pi theta. We could come up with some notation, so I could say something like theta lives in this right here, so that's the support. And so I would say theta also lives here. But it's also going to place positive mass on all of those values of theta. So what I mean is something like this. I might say this, same support, and maybe I could put or larger. It's kind of a waste of time to make it bigger, as we'll see through our experiments, but you can't make it smaller. So let's say our target looks like this. This obviously is not that example. That example has contours like this. But I'm going to imagine maybe this is pi theta, given x. I've got some mathematical equation that I can write down to do this. So this is likelihood times prior. You don't actually need to normalize it. And we'll see that in a couple minutes as well. And G is something simpler that I do know how to sample from. So the proposal, we know how to sample from it. The target, we do not know how to sample from, but we know how to write it down. So I can write down likelihood times prior all day long and come up with a tractable mathematical formula. Sampling from it means that I'm going to sample in these regions right here with area, with frequency proportional to the area under that curve. So what I mean is if I come up with a histogram representation of my samples, if I have a lot of them, it will closely resemble that curvature. So that's the name of the game in sampling. So G might look something like this. That looks horrible because G's too big. It's too tall. So let me at least make it look like it's actually a distribution and integrates to 1. So G might cover all of this space. It's going to have some tails. It's going to come down. right here, but this might be a simple distribution that we know how to sample from. And so I've made pi look complicated, and maybe G looks like a normal distribution or something like that, something that we do know how to sample from. It won't work, obviously, if I propose things. If I had something like this, let's say my target looked like this. So that's pi theta, given x. And let's say I had some proposal, and the proposal only covered that region right there. So if that were G theta, and this is not, G doesn't have the same support. So G theta doesn't have the same support as pi theta. So if I were proposing values just in this boxed region right here uniformly, I could never learn about that stuff right there. So the proposal has to place points where there could be points under pi. I think that all makes sense. Okay, let me write down the algorithm. I think we know all the components of the algorithm so far. So I'll initialize theta. I'll give it some index. That's going to be my index right there. And I'll just say that's some value that you've plugged in. So for this example that we'll be playing around with, we'll pick starting values of phi and mu. Obviously, I'll have to adhere to the nature of the problem, and I'll have to pick some starting value for mu. That can be anything, but phi obviously will have to be positive. And my proposal cannot propose negative values either. So it has to adhere to at least the properties of the target distribution. Okay. We'd have to embed an indicator into our function to vary in the support. So if I ended up proposing it, it would say that it had 0 mass in the target. So if I picked like a negative phi or something. Okay, here's the algorithm. For t goes from 1 to cap t. Step 1 is I'm going to propose from G. So what I mean in terms of this picture right here is I'm going to sample from G, and let's just say I had some starting value. Illustrate what the starting value is. It would be nice if we knew where the massy part of pi is, but in general we don't. And in a high dimensional space, you really don't know. So we might start over here, theta 0. That's going to be our first value. I just picked it. I don't know where the mass is. It's probably off into the tail of the distribution somewhere. Might be way down here. So, and then I'm going to sample from G, and G's going to pick some other value. Let's say it's right here. And I'm going to decide if I want to take that value. I'm going to do one of two things. I'm either going to stay at the same location, or I'm going to move to my proposed value. Shouldn't call that a 1 yet. I should call it a star. So we proposed it. And we're going to decide about this. And so our decision looks like this. This is the proposal. And then we'll decide. So here's the acceptance probability. This is a stochastic algorithm. It's going to be the minimum between 1 and some positive creature. So we can think of that as a probability because it lives between 0 and 1. So this is the ratio. I'm going to evaluate my target at theta star. This is my ratio of target. I'm going to compare to where we were last time, given x. And then I'm going to build in my proposal ratio. I usually call this the inverse proposal ratio because it's inverted with respect to the target ratio. we're going to flip a coin with that probability and decide if we want to move to our proposed location. I'll write that down in a second. So I want to just point out that the theta star is in the numerator over here, so in the target ratio, and theta t minus 1, comparing to where we were last time, theta t minus 1 shows up down in the denominator. And that's reversed in the proposal ratio. So they're flipped over from each other. Okay. This is going to be our updating scheme. So what I'm going to do is I'm going to update theta t, and it's going to be one of two values. It's either going to be theta star or where we were last time. So I want to just point out, we don't throw the point away, we store it. So common misconception, if you've seen accept reject algorithms, and you're just discarding things and throwing it away, pretending like you've never seen it, you do not do that in Metropolis Hastings. You keep it and you store it. What it's telling you is it's a good location, and there's mass at that point. And so it's elevating that mass at that point, at least compared to what you were proposing. It looks a lot better than that probably. So this is going to happen with probability alpha, and this happens with probability 1 minus alpha. So I do one of two things. I either store the same point, we're not discarding it, or I move to my proposed location. So let's just look at this ratio real quickly. In terms of the target, what this is saying is that if you have more mass at theta star than you did at theta t minus 1, you're inclined to make the acceptance. It looks better than where you previously were. So in terms of our graph, right here, I would look at what the mass was here, and I would compare it to what the mass was here. So this is higher than that. And so this is going to be greater than 1, and so that's going to drive up the probability. But we have to be careful. So we have to think about how we got there in the first place. And what this part of the decision rule is saying is we need to be able to move backwards, back to the original location. So where we proposed from. And so we don't want to just go there because it looks better. We also want to make sure that we can get back to that previous location. So if it's very hard to move from theta star to theta t minus 1 and do the reverse move, maybe you don't want to move there so quickly. So it's a trade-off in those two ideas. And so you've probably heard me say this before, but I think of this as like all our life decisions. We make decisions based off whatever our utilities are. And we think, if that looks better, I'm going to go. But we're careful sometimes. We want to make sure that we can come back to our previous state. So Friday night, we do that all the time. So maybe not all of us, but we think about, how do I get back to my previous state on Saturday morning so that I can get my stuff done and that I haven't destroyed everything. So maybe I'm the only one that thinks about that. So I usually tell a story like, there's all kinds of stuff I want to do with my life. It used to be, I used to want to be a motorcycle racer. And so I might go to my department head and say, hey, how about a sabbatical? I'm going to go see if I can make it in MotoGP. So, any GP fans? It's pretty niche. So, it's my favorite sport. So, Dave's going to say, go ahead, but you're not welcome back. So, I can't get my old job back. So, I might be careful and just go down there periodically on the weekend. And so, have a little bit of fun, but I'm able to come back to work on Monday. And I do think that when I'm out on the track too. So I do go down to the track and I play around. And there's a lot of guys out there that are super crazy. So, and I think to myself, I need to work on Monday. I don't need a broken leg out here. And so every time I go out there, somebody breaks something. So every single time. Broken collarbones, broken legs, broken femurs, so deaths. So helicopters come out. So I try not to be that person. So. Excited. Okay, that's what this algorithm is saying. It's that compromise, it's that trade-off. So I usually run a Metropolis Hastings algorithm right before I go to the track and decide whether or not it's working. Okay, I don't do that, but I do think in this manner. So I think that the algorithm is at least roughly intuitive. So kind of makes sense why you would make that trade-off in the decision. So we'd have to compare also, if I moved here, I'd have to compare to where I was previously in terms of G, that tail's coming down. And maybe I would say not so fast, just because this is higher than that. In terms of the way that I've drawn it, that's way higher than that thing. And the higher thing in the proposal is here. So the way I've drawn this picture, I might not make the move. So just because the target is higher doesn't mean I necessarily want to go there. And what would I be losing out on? Information over in the tables. So I want to learn about the tables of the distribution. So that's the algorithm. And this is one of the other reasons it's probably popular, is it's exceedingly easy to code this thing up, at least in simple cases. I will give you the big punchline. What a whole MCMC class is about G, and how you pick different G's. Sometimes you can't write down just a parametric density for G. You'll need a process that ends up evolving G for you. There's adaptive variations of this. There's things with very complicated processes, mixtures. So there's processes that take into account gradients. There's processes that take into account second derivatives, if you could compute them. So the modern thing is to take gradients and give it a random jitter as well, and do that random jitter in just the right way. So it turns out randomizing things is a very good idea. Okay, so I think for this class, we're going to focus on just pretty simple G's. We'll point out what some of the pitfalls are to those G's, and you'll have to wait until you take a full-blown Monte Carlo class to see all the different variants. So it's pretty cool stuff. Okay, let's run the algorithm. Let's see what it looks like. So let's come to this example right here. So xi's are coming from a normal distribution. And we want to infer this posterior distribution. We know the posterior looks like this, but I'll point out, if you went to a scientist, if they came in with some data, you went through all your hard work and you came up with a model. Okay, so this is a little bit of a fiction. So anybody could have done that, said it's normally distributed. But let's say you have some model. If you just wrote down the equation for them and said, just plug your data into that equation, that's your answer. That is not useful to any human being out there. So they don't know what to do with it. So what you would want to do is you'd want to probably identify where the mass of the distribution is, so maybe the map. And maybe you would want to identify where the 95% region is, or something like that. Maybe you'd want to identify the variance in that direction, or the variance in that direction. Maybe you'd want to identify some quantiles, or something like that. And so what I'll point out is that through sampling from that function, we can approximate all of those things. And so that's what we're going to do. So we're going to change this from a math problem to an algorithmics problem. Collect samples and then estimate everything. And the more samples we have, the better our estimates will be, so long as the algorithm is converged. So much of this conversation is about diagnostics. And I'm also going to sweep a lot of those under the rugs as well. So I'll make you aware of some of the popular diagnostics, but I'll tell you what most people do. And they usually just inspect some graphs and they look at them. So there are some more objective ways of doing things. And we'll look at that a little bit. Okay. Let me just point out real quickly, in this algorithm, the way we have it written down is I have the posteriors proportional to something, and I haven't written down the normalizing constant. This is a fabulous thing that happens in almost all Monte Carlo algorithms out there, is you don't need the normalizing constants. So this thing right here, I can just write down likelihood star given x times its prior distribution, evaluated at star. And I can do the same thing down here. I can just write down the likelihood function evaluated at where we were last time times the prior. evaluated it where we are last time. The normalizing constant cancels out in all of that. So fantastic, we don't have to do a hard integration problem up front. If we could do that problem, we wouldn't need a sampler probably. So you don't need that stuff, so that's beautiful. Okay, let me tell you about one more thing before I run this. Otherwise, I might confuse you. I want to tell you what a Gibbs sampler is. And I'm not going to prove this right now that Gibbs samplers are a type of Metropolis, and the same theory governs Gibbs that governs Metropolis Hastings. This is what a Gibbs sampler is. I haven't shown you this yet. So, Gibbs sampling. And I'll write this down more generally next time. Unfortunately, if I did just direct Gibbs, and I will have you do this on this example, it converges in one step. And so I'm going to do things very intentionally to slow down the convergence of the algorithm so you can see the nature of the algorithm. And I'm going to be doing that by imposing a very badly tuned Metropolis sampler. So when you actually do this on your homework that I'll post later tonight or tomorrow, you'll probably be like, this works way better than what Skelton presented in class. That might puzzle you, but that's the right behavior. I don't want to show you something too good for the first example. So, because when you get to harder examples, you might forget to check everything. So here's what a Gibbs sampler is, at least for our example. So it's going to be two steps. We're going to first sample from mu, and it's going to come from its full conditional. So mu t given x, and it's going to be conditioned on phi t minus 1. So this is the full conditional for mu. What we're going to do is we're going to update now the phis using its full conditional distribution. Phi is the random variable. Conditional on x and mu t. So what I'll point out is I'm taking this mu t, I'm plugging it in right there, and I'm taking this phi t and I'm plugging it in right here as we iterate through everything. So this is nested in a for loop. So I'm going to teach you two things simultaneously. So this is what's called a Gibbs sampler. So a Gibbs sampler is a sampler where you iterate through sampling from the full conditionals of a distribution. Here's a fact. This is for both Metropolis Hastings and Gibbs. I'll get a collection of values. So we're going to get theta 1, theta 2, theta 3. There's going to be some long period of time. I'm going to call this theta cap b, theta b plus 1. And I'll do this all the way to theta cap t, the end of our for loop. So I'll collect these samples. So in both the algorithms, keep in mind, at the end of the day here, theta t is equal to mu t, phi t. That's our parameter set. So that's the notation I'm using. So I'm getting pairs at the end of every step. So if I run either Metropolis Hastings, at the end of the day I get a collection of theta values, I update everything. So at the end of every iteration I have a new theta t. That happens too for Gibbs sampling. In both of these algorithms, and I'm not going to prove this in its full-blown glory, but I'll at least allude to it in this class, that Gibbs is a type of Metropolis. So people didn't know that originally. So that took until about 1994 for people to catch up that all these different algorithms everybody was peddling and learning about were really the same algorithms in disguise. George Cassell wrote a paper on it. Luke Tierney wrote a really good paper on it. And so tyranny with an I. And he kind of said, all these algorithms that we're studying are controlled by the exact same mathematics, and they are the same algorithms. So I'll point that out as we get a little bit farther along in this. So at some point, the samples will be coming from our target. So at some point, B, theta B plus 1 to theta T, the end of our loop. These are going to be distributed according to pi theta, given x. So these samples will be coming from our target distribution. This stuff right here is garbage. It's junk. Normally people call this the burn-in. And so that's your burn-in period. The cap B stands for burn-in. Let me just illustrate this for us. What I'm going to do in this problem, if we actually did do this, we know that full conditional distribution, and we know that full conditional distribution. So we know both of them. You could implement this, and it would converge real quickly. Cap B would be like 2. So what I'm going to do to slow it down is I'm going to pretend I don't know how to sample from that distribution. And I don't know how to sample from that distribution. I don't know what it is. I have no idea. I've never done any math in my whole entire life. I can't recognize it. But I know this algorithm. So what I'm going to do is I'm going to do an MH step here. So I'm going to do a Metropolis Hastings decision on updating my mu, and then I'm going to apply the same thing here. So I'm going to have proposals for both of these, and I'm going to update them in sequence. And it turns out, since everything is Metropolis Hastings in disguise, you can combine those two algorithms. That's called Metropolis Within Gibbs, and that's what most people do. So that's the common thing that people do. A lot of people will just say they're running Metropolis. So be more specific about this next time. Let me just show you what this looks like. And then next time we'll scour through this code. Try to understand what it does. So here's my code. I'll post this online so you can look at it. But what I have built in here are some toggles. I'll tell you what thinning is later. Your step sizes are going to have to do with the proposal variance, so I can tune that. So I'm going to be using what's called a normal random walk proposal. So I'll tell you about that proposal next time. There's a burn-in period right here where I throw everything away and I discard it at the end of the problem. And then I have some initializers. If I plugged in the actual truth, that would be cheating. But the algorithm would be stationary right away and cap B would be 1. So we won't do that. I'll pick some different things and we'll kind of press on this code a little bit and see if we can try to break it. So everything just runs in a for loop. And I'm going to have these 2 steps. I'm going to update mu. That's this step. I've put everything on a log scale. And I have some commented out stuff that if I didn't put everything on a log scale, this code would deteriorate pretty quickly. So that's done for numerical reasons. And I'll walk you through that later. I evaluate some ratio on a log scale. So on a log scale, a ratio is a difference. These are actually log proposals and log. I have to walk through the details of all of this to show you what it is. I do the same thing for variance down here. So if you want to come through and look through that code, go ahead and do it. But I wouldn't bother yourself too much. So on Monday, I'll tell you all about this code. So let's just run it. And then we'll get out of here. So I've already picked some values for the truth. So true mu, I picked to be 7. True sigma, I picked to be 2. I'll generate some new data right here so we can see new data being generated. So I'm going to generate 31 points from a normal with mean 7 and variance 2. So actually the standard deviation is 2. So the variance is 4, so the precision is 1/4 in my example. We'll slow that down next time. Now I'm just going to run this code. And here's what it does. So there's my starting location right in the middle. That's the red dot. And it runs for a while. We get rid of that. Come back and look at this. In 2 dimensions, after every iteration, right here, I have a new point in that plane. So phi is in that direction, mu is in that direction. So we can kind of see this trajectory that it's walking down. It looks pretty funky, like the way that it's walking through those contours. So that has something to do with the shape of the contours. So it's converging in terms of mu faster, and it's converging to phi. So it ended up walking down this diagonal path from my starting point that's up in the upper left-hand corner. It converges in on mu, and then it shoots down and it converges in on phi. All this stuff right here is junk. This is our truth down here. The red dot's down there. You might not be able to see it right here. And we could zoom in to all of that. What I've done is I've ripped off all of this stuff, the burn-in period, and I've plotted the samples after it's burned in. And those samples look like this. So these are samples that resemble that contour. And it kind of has this rounded out triangular shape that we were talking about before. And I can end up plotting the marginal distributions as well, but let's come back next time, talk more about these details. And then I'm going to walk you through the theory on how you can prove that a Markov chain algorithm is valid and will converge. But let's just go through the practicalities first. That'll be on Monday probably. We'll get started with the theory. We probably won't round out this whole conversation until the end of next week. Enjoy the fall break, you guys.